Okay, let's unpack this. We talk all the time about how incredible these AI agents are at, reasoning and planning.
Right.
But there's this huge bottleneck. When it comes to actual scientific discovery, going from a theory to a real-world action, they just stall. Why is that?
It's because science is so siloed. The tools are all over the place.
Yeah.
You've got, say, a genetics package here, a chemistry database over there, maybe a robotics API.
And they don't talk to each other.
Exactly.
Yeah.
They all speak different technical languages.
Mm.
So an AI can have this beautiful, elegant plan, but if it doesn't have a standard way to actually run the experiment,
Oh, cool.
it's just a planner with nowhere to go.
So it's brilliant in theory, but it can't actually do anything.
Precisely. And that's the gap our sources today are really digging into. They lay out this incredible open source ecosystem. It's called ToolUniverse.
ToolUniverse.
Yeah, and it's designed specifically to solve this problem and, build what they call true AI scientists.
That's a bold claim.
It is. The whole mission is to democratize this,
Right.
to create one shared environment that brings together all the tools, all the data, all the analysis.
And what's the comparison they make? Is there a historical parallel?
There is, and it's a great one, genomics research.
Okay.
Before they had standardized platforms, every lab was just kind of reinventing the wheel.
Hmm.
But once that infrastructure was in place, it just exploded into this high-throughput community effort. ToolUniverse wants to be that for AI-driven science.
So this isn't just another tool. It's meant to be the operating system for an AI research assistant.
That's a perfect way to put it. And it's designed to be model agnostic, which is key. It acts as a universal wrapper.
Meaning you can plug anything into it.
Pretty much.
Yeah.
Any language model, any reasoning agent, open source, closed, whatever, you connect it, and it instantly gets all these real-world scientific abilities. And importantly, without needing to do any expensive fine-tuning on the model itself.
I see. So that really lowers the barrier to entry. You don't need $1 billion to train a custom science model.
You just plug your model into the ecosystem.
And how big is that ecosystem? I mean, tools can mean anything.
It's vast. Right now, it gives you standardized access to over 600 tools.
Wow, 600.
And we're not just talking about simple APIs. This is machine learning models, robotics packages, scientific databases, visualization tools, and really importantly, safety tools that require a human to sign off on things. It's the whole workflow.
That sounds incredibly powerful, but also like an engineering nightmare.
It is. That's the core challenge, right?
Yeah.
Heterogeneity. You have text data, genomic sequences, protein structures.
All different.
All different. Some tools run locally, some are on the cloud, some talk to a robot in a lab. So if an AI has 600 options, and a lot of them do similar things, how does it pick the right one? How does it format the data correctly?
It's like the AI needs a universal translator to turn its ideas into action.
And that's exactly what they built. The core of it all is something called the AI Tool Interaction Protocol.
Oh.
The source material compares it to HTTP for the internet. It's just a standard set of rules for how to define a tool and how to talk to it, no matter where it is or what it does.
So the AI doesn't talk directly to the tool. It talks to the protocol.
Yes. And the protocol breaks everything down into just two simple operations. The first is find tool.
For discovery.
Right. The AI decides it needs to do something, like calculate the molecular weight of this, and the system maps that plain English to a very specific machine-readable format the AI can use.
So no more guesswork for the AI. It just asks what's on the menu and gets a structured answer back.
Exactly. A structured menu is the perfect analogy. And the second operation is call tool. That's the execution. It takes the arguments from the AI, sends them off, runs the tool, and brings back the results in a nice uniform format.
And what's in that standard format?
It's two main parts. You have a specification schema that describes the function, the parameters, the output, and then an interaction schema, which defines the one single way to make the function call. All 600 plus tools are forced into that format.
Okay, here's where it gets really interesting for me. Because we've seen frameworks, like LangChain or AutoGen, that can orchestrate tools, but the sources say ToolUniverse is something fundamentally different.
It is, and that distinction is so important. Those frameworks help a model use tools that already exist. ToolUniverse manages the entire life cycle of the tool.
The entire life cycle.
From discovery and use, all the way to optimization and even creating new tools from scratch. It's built on 6 core components. Let's start with just finding the right tool with the tool finder.
Right. With 600 options, that's not trivial. How does it search that huge space accurately?
It uses 3 integrated strategies. First, for speed, there's a classic keyword search. They use TF-IDF scoring to make it precise, and they add what they call a hierarchical bonus.
A hierarchical bonus? What's that?
It just means if your search term matches the tool's actual name, it gets a way higher score than if the word is just buried in the description somewhere. It helps bubble up the most relevant stuff fast.
Okay, that works for simple searches. But what if I ask something really complex, like, find a tool to analyze protein secondary structure from an amino acid sequence?
That's where the second strategy comes in. LLM in context search. It actually uses the LLM's own reasoning.
Ah!
It builds a prompt with your complex question and a few candidate tools, and then asks the LLM which one of these is the best semantic fit.
The downside must be speed, though, and cost.
Definitely. It's great for understanding, but it's slow. So for massive scale, they have the third strategy, embedding search.
Vector search.
Exactly. They fine-tune an embedding model just for this. It turns all the tool descriptions and your query into vectors, and then just finds the closest matches in a vector database. It's how you get both semantic accuracy and scale.
So the tool finder gets you the right tool, but science isn't just one step. You have to chain things together.
And that's what the tool composer's for. It's the engine for building these complex workflows. It can do things sequentially, A then B, or in parallel, like running 10 literature searches at once.
And can it adapt?
Yes, and that's critical. It supports feedback-driven execution. So the agent can look at the results from one tool and then dynamically decide what to do next.
Let's talk about integration. What if I'm a big pharma company? I've got my own secret proprietary model for predicting toxicity. I want my AI to use it, but I can't just upload it.
That's the job of the tool manager. It uses something they call the Model Context Protocol, or MCP, for exactly that scenario. It lets you register remote, private tools so they act just like any other tool in the ecosystem, but without ever exposing the con or the data.
Okay, now for the part that really blew my mind. The part that goes way beyond other frameworks, creating and refining the tools themselves.
Here's where it gets really interesting. You're talking to the tool discoverer.
Yeah.
This isn't just wrapping existing code. This is a system that can generate entirely new tools, the specification, the executable code, everything from just a natural language description.
Wait, hold on. I can just tell the AI, I need a tool that calculates small molecule solubility, and it will write the Python code for it.
It will write the code, and then a whole multi-agent system kicks in to validate it. It runs tests, checks that it follows all the rules, and refines it. So if the AI finds a gap in its own capabilities during a project, it can just fill that gap itself.
That iterative quality control is everything. You need to trust these tools. Which brings us to refinement. What if a tool's description is just confusing?
That's the tool optimizer. Its entire job is to constantly improve the existing tools. It generates test cases, it analyzes how agents are actually using the tools in the wild, and it refines the documentation until it meets a really high-quality score, like an 8 out of 10.
Why that score? What happens if it's bad?
If the spec is ambiguous, the AI is way more likely to use the tool wrong past bad arguments, misinterpret the results. That quality score ensures the tools are rock-solid, reliable for the agents.
This whole system is amazing. To really see it in action, let's get into the case study they ran, autonomous drug discovery for high cholesterol.
A perfect example. They took the Gemini CLI agent and hooked it into ToolUniverse. And the first step was target identification. The AI started using literature mining tools like EuroPMC, and then combined that with biological profiling tools like OpenTargets.
And what did that first pass turn up?
It correctly prioritized HMG-CoA reductase, which is the famous target for statins. But here's the cool part. It also analyzed tissue data and saw high expression not just in the liver, where you want it, but also in the brain and the GI tract.
So it identified the risk of off-target effects right at the start.
Immediately. It wasn't just find the target, it was find a target and, by the way, try to avoid these other tissues.
That constraint is everything.
It guided the whole rest of the process. For stage 2, initial screening, the AI went to drug bank, profiled existing drugs, and it picked lovastatin to optimize, specifically because it's known to have those neurological side effects.
So the goal was clear, make a better lovastatin. Time for the prediction models.
Exactly. This was the molecular optimization and prediction stage. The AI went into the ChemBL database and pulled all the structural analogs of lovastatin,
Analogs.
molecules that are very, very similar in structure. It was looking for things with a Tanimoto similarity over 0.8, which basically means they're very close structural cousins.
Okay.
It then ran this list of candidates through 2 specialized ML tools.
Which ones were those?
It used one called Boltz-2 to predict binding affinity to the target, and another called ADMeet AI to predict the pharmacological profile,
Yeah.
including the all-important blood-brain barrier, or BBB, penetrance.
Right. So you want high binding for potency, but low BBB penetrance to avoid those side effects. What did it find?
The results were fascinating. First, it validated itself. In the results and validation step, it identified pravastatin and correctly noted that it has lower BBB penetrance than lovastatin.
Yeah.
It's a known fact, so it proved the system was working.
And did it find anything new?
It did. It found a new candidate molecule, identified by its Gembl ID, that was predicted to have higher binding affinity to the target and reduced BBB penetrance compared to lovastatin.
So a potentially better drug.
Potentially.
Yeah.
But in the real world, there's always one last step.
Intellectual property.
You got it. The final stage was patent assessment. The AI used PubChem API tools to check for novelty, and it found patents from 2019 and 2021. The molecule was already claimed.
Wow. But just think about that whole chain. The AI went from a high-level research question to identifying a design constraint through molecular screening and ML-based prediction, all the way to a patent search.
In a single, self-directed workflow, there's a profound proof of concept. And the real impact here is lowering the barrier to entry. This moves AI research from these one-off bespoke projects into a community-driven, reusable ecosystem, just like genomics.
So if a researcher out there listening wants to get started with this, how do they do it?
It's designed to be really lightweight. You can connect something like GPT or Claude to it, often with just a few simple instructions. It's also a powerful training ground for more specialized agents, like Teak's agent, which can use it as a real-world environment to practice and get better through reinforcement learning.
And the sources suggest it's also a test bed for what comes next.
That's right. The next step is integrating these AI scientists with actual lab automation hardware. But it's also about safety. The system has human-in-the-loop tools built in from the ground up, so an expert has to sign off on critical steps before the AI can proceed.
And what about the quality of the tools themselves? Are they trustworthy?
They have a rigorous validation pipeline. Every tool is tested, reviewed by human experts, and automatically optimized. And they prioritize tools from trusted sources, like the NIH and the FDA. That verifiable quality is essential if you're going to do real science.
It really brings it all home. This provides that critical missing piece, the bridge that lets an AI model go from just reasoning about text to being a true collaborator in the lab. It turns thought into verifiable action.
It does. And if you think about the long-term implications, especially with things like the tool discoverer, I mean, the pace of discovery could accelerate dramatically.
Yeah.
But the sources also touch on biosecurity.
Right.
Because if you make it this easy for an AI to generate and execute novel scientific protocols, you have to ask the question, what governance structures do we need to build into these ecosystems right now to make sure that this incredible creative power doesn't accidentally accelerate biorisks faster than we can build in the guardrails and the human oversight? That's the balance we have to strike as this all scales up.